how would that split into two clips or not? Okay. All right. So what we have over here is, look at this one. If the surface that I am interested in is this sphere right here, so think in 3D. And let's say you have an electric field that's just coming out of it. What do you think it will happen to the net flux on this sphere surface?
Positive.
Yeah, it's out, right? It's out. So
Oh,
electric field try to come out from it. So flux should be positive in this case. Does that make sense? Okay, come here. Next one. So now you have a tube, or you can have like a cylinder over here. So you have a cylindrical surface. Then the surface that we are talking about will composes of here, the top surface, the bottom surface over here. Let me sort of slowly writing this down. And the side surface, the one on the side. Does that make sense? Okay. So imagine what is going on the top part. Electric field seems to sort of like piercing in. It's trying to enter the enclosed volume. So on this surface alone, on this surface alone, this will give you a negative flux just on this surface. So yeah, just on this one. So let me call it the top. But then in the bottom surface over here, on the surface in the bottom, electric field is coming out, try to escape from the enclosed volume. So on this surface, you're going to get a positive flux in the bottom. Does that make sense? Get that a little bit better picture of what is going on. And now on the side, you can see that if I draw some sort of like an overlay area vector, the area vector of the side surface will come out like this. So I'm trying to draw like in a perspective manner over here, right? However, the electric field is going downward. So there's nothing piercing through the side surface whatsoever. Nothing. So in that case, the flux for the side surface will be zero. So that's the idea, right? That's what we had sort of like try to come up with the idea of like, okay, we're going to calculate the flux on this surface, that surface, and overall surface. And then once you sum them up, that will be your net flux. So you can say sum of those will give you the net flux on this closed surface. Cool? A little bit better. Okay, let's do one on the right over here. It's a cube. Think of it that way. So you have the left surface. You have the front surface. You have the top, the bottom, and the right surface. Something like that. Okay, 6 surfaces total. But what you can see over here is going to enter the left surface. So right there, that's where it's going to enter. Just on that surface alone, you will receive a negative flux right there on the left. Let me put on the left right here. And then when you look on the right, this is going to be the outgoing flux on this surface right there, because it's trying to escape from the enclosed volume. So if you look just only on this surface, you will get positive flux on the right surface. Does that make sense? And then when you look at the top, the front, the bottom, the back, there's no penetration of these lines through those 4 surfaces. So that means you're going to get zero flux on the back, and zero flux in the bottom. That's just, let me call it equal to 0.
Question, sir.
Okay, yeah, go ahead.
What if the electric field is curved?
Yeah, okay, you have to calculate those. Yeah, it can be curved.
Oh.
Yep. So it just makes more complicated, because when it's curved, then it makes some angle with the surface, and that's where the dots product comes in. Does that make sense? Right now it's easy because
Okay.
I'm trying to give you a simple geometry, It's like electric field just going through perpendicularly to the surface. So this is the scenario that the electric field going in the same direction as the area vector. So that makes things a lot easier over here.
อาจารย์
Yep.
I think you might want to look into the chat.
Yeah, I can see you send me what? A Google
The accumulation of
Gauss's simulation. Okay, let me see. Is it like something that can run 3D?
yeah, it's 3D.
Ah, okay, cool. All right. Okay. All right. We'll get back to this. It looks it is not loaded yet. Okay, here we go. Oh, that might works. Whoa, 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 whoa. Yeah, let me see. Let me see. All right. So what we're going to do next is we're going to calculate the flux through a volume and see how it's done. And then when we have a chance, we'll get back to that simulation. It looks nice though. It's a three-dimensional stuff. All right. You send me 2 of them. Is that right? Okay, cool. Is that scalable somewhere? Okay,
Yeah,
anyway,
it can be.
we'll play on that in a little bit. Okay, but it looks cool. Thank you very much for the link. It looks nice. Okay, guys, so let's practice how to calculate this. All right, so let's try this exercise and see. We'll go back to your friend's suggested site and see, you know, would that be sort of synchronized between what you learned over here doing the calculation and the three-dimensional simulation that looks like it's a cool drawing over there. All right, guys. So let's put that into like a real quantitative calculation over here. You have a uniform electric field E oriented in the X direction. Find the net electric flux through the surface of a cube of H length L. Oh, okay, that's fine. Oriented as shown in the figure. They want the net flux. Even though everyone knows that net flux will be 0. You guys with me? Because we have already discussed this. It's pretty much the same as this one. The reason we can tell right away is the net flux is supposed to be 0 because it's going to enter and leave with the same amount of electric field lines. You guys with me?
Okay.
Okay, sounds good. So what you have over here is just like, oh, John, we can sort of take these surfaces into, okay, here, this is the front. And there will be one on the back. These are the only 2 that there is a non-zero flux going through. You guys with me? Right? Because the electric field is just piercing through these 2 surfaces, not the other 4. Okay. Does that make sense? Okay. The top, the bottom, the front, and the back will not get any flux because electric field is just sort of like passing by. There's no angle to it. So there's nothing. Or in speaking in terms of the area vector. Oh, sorry. That's wrong. There you. Yeah. The top surface area is perpendicular to the E. Same thing with the front, the bottom, and the back. So the only thing that you need to worry about is, so the net flux is going to be the flux on, let me call this the green, right, on the left surface and the right surface. Good. Okay. The left is in the green. Oh, that's blue. I have problem with the blue and green here. And the right is the yellow right there. Nice. Okay, let's start from the left. Oh, let's start from the right first, shall we? Because the reason I want to start from this, because it's easy. Look at this. The area vector must point perpendicular and outward from the enclosed volume. So this is the A right vector. What is the magnitude? Of course, length times width is going to be L squared. What is the direction? Because it's pointing in the X direction. Let me put this I hat. You guys with me? Okay, that is the area vector of this right side area surface area. And now because the electric field over here is pointing in the same direction, I can write this as E, some magnitude, and also I hat. You guys with me? It's pointing in the same direction. So what I can conclude is that these two making zero angle between each other. They're pointing in the same direction. So what I can say is now the flux on the right is going to be E dot with the A on the right. And it's going to be the magnitude of E times the magnitude of A and the cosine of the angle between the two. Electric field E has a magnitude E that's given. The magnitude of the area is just L squared. And the cosine theta is going to be cosine 0, and that is 1. So the flux on this surface is positive E L squared. Oh, they use a capital L. Sorry, guys. So let's change it to small L then. Sorry. All right. But anyway, so what you're seeing over here is, can you see? Whenever the electric field is pointing in the same direction as the area vector, you have a positive flux. And what does a positive flux means to you? It means that the electric field is escaping from that surface or from the enclosed volume. It's an out flux. Better?
Okay.
Maybe. Try again. Let's look on the left. Flux on the left. What you can see over here is now your area vector is going to point backward, but you still need to be perpendicular to the actual surface anyway. So let me call this, of course, the A left vector. What is the magnitude of this one? Is still the length L, the width L, so it's going to be L squared. What about the direction? It's point in the backward X direction. So let me put negative I hat. You guys with me? However, electric field is still the same electric field anyway, so there's no change right there. So all I need is now I know that from these two, the angle theta between these two, let me put here and here, is going to be 180 degrees. Okay, so the net flux on this left surface is going to be E dot A left. And because, I mean, if you want to use the cosine theta, you can say it's a magnitude of E L squared cosine 180. But if you use the IJ notation already, you can see that you just take the vector A dot with the vector E, you get a negative anyway. You see, there are two approaches here. It depends on how you would like to use your vector, the mathematics that you learn from the vector stuff. Yeah. If you write it in terms of I already, one is pointing in a positive I, the other one point in a negative I, you just multiply them, and then you have a negative side popping out as well. Or you can take the magnitude of E times the magnitude of A and take the cosine of the angle between the two. At the end, you get negative EL squared. And what does the negative flux means? It means on that surface, electric field is trying to enter the enclosed volume. Yes, and that is done, guys. The sigma net flux is 0.
Okay.
This will sort of like step up a little bit in terms of like how to calculate the flux, yeah, quantitatively. That's what we're trying to do right here. Feel a little bit better now, I hope. One more try. Okay, next. Okay, everyone still feel good here? No? All right, guys. Now get more complicated here. Let's do a tilted surface. There's some sort of like slanted surface over here. Consider a closed triangular box resting within a horizontal electric field of magnitudes given. Okay, so you have 10 to the 4th Newton per Coulomb electric field pointing from left to right horizontally. Calculate the flux through A, vertical rectangular surface, B, slanted surface, and the entire surface of this box. Okay, so let me highlight once again. Let me use color to help. The vertical, let me use this green right here. So this is your vertical surface that we are talking about right there. Okay. And the slanted surface, let me use blue then. The slanted surface is going to be this one right here, the one that makes some angle with the electric field right there. And of course, partially is going to be the entire surface. So you have to include the front, the back, and the bottom. Okay, so that's a question comes in. As long as the electric field is parallel and uniform, it should be fine. Correct. That is the easiest case possible. When the electric field is uniform and is already point in particular direction, then you don't have to worry too much. Like this one, electric field is uniform, so you only have to worry about the orientation of the surfaces. Okay, let's try this one, guys. This will help sort of like checking your understanding a little bit. So let's start from part A. What about the vertical rectangular surface, guys? All right, so let me highlight this one. So it's the green area over here that we are interested in. So first of all, you have to be able to identify the direction of the electric field. I'm sorry, the area vector first. So over here, area vector point outward from the enclosed volume. So that means your area vector is going to point backward like this. Let me call this a vertical vector. Yes? Okay. And I can write it in a different fashion over here. I can say the magnitude of the A vertical, which can be just written as the A vertical, the subscript V without the arrow on top, is going to be just the height times the length. So it's going to be 0.1 meter times 0.3 meter. You guys with me? That is just the magnitude of this area, the green surface area right here. But now you can tell by the direction that is point opposite to the electric field. So that means the angle between these two is going to be 180 degrees. So let me figure that out. The flux on this vertical surface, let me use subscript V as well, is going to be the electric field dot with the A sub V vector. But then you say it's going to be equal to the magnitude of the electric field times the magnitude of the vertical area over there times the cosine of 180 degree. Yes, okay.
Okay.
Very good. So with that, it's just going to be negative as expected because electric field is trying to enter the enclosed volume of this box. Electric field line, I mean, is given in magnitude. So, I mean, okay, let me substitute here just for clarity. So it's going to be 10 to the 4th Newton per Coulomb there. And then times the area, which is already calculated up there, 0.03 square meter. Okay, let me sort of summarize over here. And that's it, guys. That is done. That is the flux, is a negative flux, is coming in this much. Okay, now try again. What about on the slanted surface? So let me name this slanted surface A subscript S. I have to draw the area vector first. So it's going to point perpendicular to the actual surface. That is your A sub S vector. Yes. All right. What is the magnitude of this one? You can say the magnitude of A sub S vector is going to be the whole here. It's going to be hypotenuse over here multiplied by this 30 centimeter depth or length. So because I don't want to do Pythagorean theorem at this point, so let me call this, let me call B at this point right now. That length, the hypotenuse length over there, that's B. So it's going to be B times 0.3 meter. That is your area. Okay. So now, just to make things a little bit clearer, let's look sideways, shall we? So you have vertical surface here, sitting there. You have slanted surface right there. Over here. Whoa, 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 whoa. Not good, not good. There you go. Okay. And then you have the bottom surface sitting right there. So when you drew that area vector, that is your A sub S vector perpendicular to the actual surface. And this in comparison to the electric field that going horizontally right there. Okay, this is a side view of the situation that we have. on hand right now. But because the problem say the angle on top right here is 60 degree, so you can say this is also 30 degree. So that 30, this will give you 30 degree, and it will give you back 60 degree right here, 60 degree. Does that make sense? Okay, this is 60. So that means the angle between A sub S vector and the electric field vector is 60 degree. Now I can go ahead and say part B, flux that going through this slanted surface over here, the whole thing. So let me highlight blue over here for you. Oh, that's green. Sorry. I have a problem with this too. Okay, here we go. That's your slanted surface right there. There you go. You want to figure out how much electric field lines is piercing through that blue surface. So what you say is going to be equal to E dot with the A sub S. But you just said the magnitude of the E is E. The magnitude of A sub S is A sub S. Haven't done anything. And then you take the cosine 60, because that's the angle that A sub S and E is making. 60 degree. Okay. And now here is the key, guys. Almost done. Almost done. E is no big deal. It's 10 to the 4th Newton per Coulomb. That's done. Now A sub S, we took it from there. The magnitude of A sub S is B times 0.3 meter. Okay. And then you have a cosine 60. We haven't figured out the B just yet. But my question is, do we need to figure out the B, the length of the hypotenuse there? The answer is no. Do you notice something over here, guys? What is actually B cosine 60? Look one more time. Your B is actually the length of this hypotenuse right there. So let me highlight that. Blue here. Here, let me sort of make it thick, super thick over there. That's your B, right? The angle is 60 degree. This angle is 60 degree. But then what you want is you want B cosine 60. What is this? B cosine 60 is this length right here. You guys with me? Yes.
Okay.
When is B cosine 60? It's just the height. Why is the height? It's because this area over here is the components of the slanted surface that is perpendicular to the E, or speaking in terms of the vector, A sub S, when you do the cosine 60, will give you this component right here. Let me draw it in black. Here, this is A sub S cosine 60. Is the component that is pointing in the same direction as the electric field vector. However, every time that you look at the area vector, it must be representing a real surface that is perpendicular to this vector. So it's going to be this direction of the area. You guys still with me? So this is what it means that we started talking about this earlier, that's what you want. You want just the components of the area that actually the electric field going through in the perpendicular fashion. So when you speak in terms of the area vector, you only want the components of the area vector that is parallel to the electric field. And this is exactly what we want. So that's why I don't need to calculate that B length at all. It's eventually going to give you back 0.1 meter. And can you notice that, well, Ajahn, it's exactly the same between the two? It has to be because when you look at these two surfaces, on the green, the vertical surface, the electric field lines try to enter the box. But then eventually they all leaves the box with the same amount. When you say the same amount, you can look from this figure over here. You have what? 1, 2, 3, 4, 5, 6, 7, 8, 9. I mean, the real one is not 9, but what I'm saying is whatever the electric field lines that comes in from the vertical surface, they all leaves on the slanted surface. So no doubt, I mean, you can guess what should be the part C answer. Because there's no flux through the front, nothing. Flux through the back, nothing. What about the bottom? Nothing. You guys with me? There's no penetration of these electric field lines through the front, the back, and the bottom. So the net electric field through this whole box is only going to be flux through the vertical and the flux through the slanted surface. There's nothing else. But because these two are exactly the same, once again, the net flux is 0.
Okay.
You guys okay with this so far? Okay. It might not be, okay, your question is a little bit, we'll get better over time. All right, one more try. This one. If you can answer this one, I think I'm happy. This is going to be the hardest of the day. But if you get it, it will be simple from now on. For your question about irregular shape, of course, it will be much harder. However, is this irregular enough for you? A cone shape now? No, this is not easy because it's three-dimensional stuff. So let's take a look at this. A cone with base radius r and height h is located on a horizontal table. A horizontal uniform field E penetrates the cones from left to right as usual. Determine the flux that enters the left-hand side of the cone. They only want half of this cone surface. They want just the left side of the cone. They don't want the whole thing. They just want the left side. So let me sort of break this into two parts, the left and the right. Okay, here we go. All right. I only want the left portion of this cone. I don't want the right portion of this cone. All right, I'll have you look at this problem and think for a minute. How do I unfold the cone? See, the hardest part of this problem is, well, Ajahn, you just told us that I need to draw an area vector, right? So the area vector has to be perpendicular to the actual surface. Well, Ajahn, wouldn't you be crazy right now? You have to like, what is going on here? You have to draw that crazy area vector. Oh, that doesn't look good. This one, oops, sorry. This one doesn't look good. Like you have to draw all the area vector around this just to calculate. That's perspective is bad, sorry. Okay, my bad. Okay, it had to go like this. I think somehow, yeah, some like this. Okay, 3D. Okay, something like that. And more, Ajahn, how would I know the angle between this vector and the E vector? Like you guys like, okay, this is like crazy. How can I do that? The answer is right here, guys. Think carefully. The key point of this flux calculation is E dot A, right? This is the key for today's lecture. We want E in the direction of A or either A in the direction of E, right? One way or the other. Just pick. Now, electric field is pointing in the same uniform direction, left to right. No matter how crazy this line is, I don't care. I only want the components of the area vector that is parallel to this E. Speak in terms of the real surface area. I only want the components of the real surface area that is perpendicular to the E. You guys with me?
Okay.
So my question is, what portion of this left side of the cone portion that is perpendicular to the E? What do you think? It's the shadow of this cone. You guys with me now? So you can imagine, like, you can think of the E directions to be direction of the light coming from a flashlight, for example. You shine this flashlight onto a cone. What is the shape of the shadow? The shape of the shadow will look like a triangle that I just drew over there. Yes. And this shadow is perpendicular to the E. Perfect. That's what we want. So that's my purpose of talking you through how this process is over here. You look at this one. Remember this slanted surface calculation that we just did? If you imagine that the E electric field line is just the direction of the light, you shine the light onto this slanted surface, it will cast a shadow in the shape of rectangle. This is the shadow of that slanted surface. You guys with me? So over here, you don't need to go crazy like figuring out the angle between the surface of the cone and the electric field vector. All you care about is just the actual surface that is perpendicular to the electric field, which is just a triangle. That you know, oh, the base is just 2r, and the height is still the height. So you know exactly the area of this triangle is going to be the half, the base, the height. 1/2 times base times height. That give you the A. With me? Okay, cool. All right, so 2 cancel, that's RH. And now the only thing left is just, okay, I'm thinking about the direction. They just only want the left side of this one. So that means you are talking about the side that is still point against the field. It's still point backward. So it's just like you just only want the component of this black shadow that is still point to your left. So overall, that means you only care about the one that actually is anti-parallel to the E. So that means the angle is still 180 degrees. So overall, what I'm saying is the flux for the left side of this one is going to be negative E times the area of the triangle. Let me put like a subscript black triangle right there. Does that make sense to you?
Okay.
And that is just negative E times R times H, and it's done. And if you are interested in, like, Azan, what about the flux on the right-hand side of the cone? Of course, it's just going to be the same shadow, but you just only take the component that actually is on the right side of this one. So that means it's just going to be the component that actually point in the same direction as E. So with that, flux on the right will be positive EA of that triangle. And that is positive ERH. And once you combine these two together, the net flux once again turns to 0, because you understand from this whole thing that electric field lines come in from the left, and all of those lines leaves the enclosed volume on the right side. Nothing left behind. There's no leftover. There's nothing in there. So the net flux in this cone, 0. There's no flux in the bottom for sure. Yeah, because there's no penetration of the electric field line through the bottom surface at all. Sounds good?
Okay.
I mean, I hope you're not exploded, or that some people already left the room. Not good. Okay, so let me ask you one question, for example, just to make things clear. I don't know, would it be clearer or just getting more confused? So if, okay, I have an electric field going through my face right now, okay? I want to know how much flux is entering my brain. I mean, my brain, I mean like my internal volume of my head right now. How can you calculate the amount of flux if the flux is just uniform, just going straight to my face? My answer is all you need to do is just cast a shadow of my head. It will like a shape of my shadow on the back. You will take that area, multiply by the electric field. That is going to be the amount of flux that enter my head. Does that make sense?
Okay.
Okay, so the concepts of the dot product, it turns out to be the exact same concepts of finding the projection of an area. Same thing. So I don't know if some of you have already taken some of the vectors or some of the, I don't know, dot products in the geometry analysis and all this stuff. They will call this a projection operation because this is the way that you can project an area onto another surface area. You only want to know like, hey, what is the size of the shadow of this and on and on. So that's why we call it a projection. I think you use this word projection many times. Here, there you go. F, S. In the work calculation, what you did was just you project the vector F on here. See? So that's why F cosine theta is the projection of the F onto S. It's the projection operator. Okay, sounds good. That's a question comes in, but don't brain have folds. It will really hard to calculate, I think. Here's the key. No matter, well, when you say a fold, as long as it doesn't really twist and make some like complex fold or anything, it's just curved. If it's just curved, then you don't care. Only all you need to care about is just the shape of your shadow. That's it. But of course, if your surface is really complex, like you have like a fold and then there is like some sort of like a layers of the surface, so this concept will not work. So you need a simple surface. Simple surface means the surface is still, I mean, it can be as crazy shape as you like, but there must not be like an overlap of the surface or there's no some sort of like a, you know, double folded portion of the whole thing. It still has to be like a simple surface to make this concept of projection work. Okay, does that sound reasonable? Okay, so you still have that shadow techniques. Yes, question please. Yes.
What if the electric field hit in a not in a difficult way, like a kicking
Yeah,
degree?
if electric field is like complex, you saying?
No, it's still parallel, but it's like hit in a different angle. Yeah, kicking degree.
It will be just harder to analyze, that's all. But the concept's quite the same, I think. But now you have to figure out the shape of the shadow in the direction that is perpendicular to the field. The shape will look just worse, that's all.
Oh, okay.
Right? For example, if you try to shine the light in different direction, think of it that way. So let's say if your electric field go in this direction, right? Then all you have to ask is what is going to be the shadow of this cone on the screen that you've placed it here. So the shape will be a little bit harder, but of course it's going to be some shape. I don't know what shape it is.
Yeah.
Right. But if you can figure out the shadow of that, I mean, the area of that shadow, then that's it. You take the area of the shadow, multiply by the E, you get the flux in that direction anyway. Yeah. Okay. All right. So I hope you sort of like see something. And then what I would like to end today's lecture with is this. And I hope by vaguely understand that concept of flux, the Gauss's law is simple. Seriously. Like this. Who generate this field? Of course, charges, right? Because positive charge have electric field coming out of it. Negative charge have electric field going towards it. So for an electric field to happen, there must be some charge responsible for it. And Gauss said, if in an enclosed surface, I mean, sorry, a closed only, sorry. If in a closed surface, you can figure out the net flux. Whenever there is a net electric flux, there must be charge in there. You guys with me now? Okay, let's go back to this one first. Here. Right. Simulation, please. Wait for the simulation. I think that simulation will come clearly after this. So you think about this, guys. First one will clear things up quite a lot. You look at a sphere. And then you say, but Ajahn, there is a net positive flux out of this sphere. What do you think it will happen inside this sphere? See, it's common, sort of like common sense in that there must be something generating this electric flux inside this sphere. Does that make sense to you? And that's why Gauss said, if you have a net positive flux, there must be net positive charge in there too. Try next one. Well, Ajahn, the second one, there is a flux coming in, the same as a flux going out. There's nothing left. I mean, nothing left. I mean, there's no net flux inside this closed surface. That I can guarantee you, charge in here must be zero. Because there's no evidence of having any positive or negative flux. It's zero. So when you have a zero net flux, mean it must be zero net charge. So that means these electric field that come in and go out must be generated from somewhere else. So that means the charge that's generating this one must be lying around somewhere outside. And we're eventually going to end someplace outside. There must be negative charge waiting for this field line to end. But there must not be anything inside this cylinder at all. Does that sound reasonable now?
Okay.
Yeah. So if you like this, then Gauss said, yeah, if you know how to calculate flux, flux will link to the charge inside one-to-one. One-to-one means, I mean, linearly. And of course, because we want to make things like in an SI system and we didn't introduce any constant in front of the flux equation before, now we need it. And that constant is epsilon naught is right here. So back in the day of the Coulomb's law that we said, I noted briefly that K can be written as 1 over 4 pi epsilon naught. That epsilon naught just show up right here. Okay, but now you can see that that's a simple idea of the Gauss's law. Flux comes from charge. If you have net positive flux, there must be net positive charge. If you have net negative flux, there must be net negative charge in there. If you don't have any net flux, inside that closed surface must have zero net charge. Does that?
Okay.
So that's what we are going to utilize and apply next time that we see on Saturday. All right. But before we leave, I think your friend just posted a very good link and it's a 3D simulator. So let me show you that right there. Here we go. All right. Is this one? Okay. Yeah. Is this good?
Yeah.
You guys can see it. Let me zoom it in. There we go. Yeah. So
you can drag.
I cannot rotate it though.
Or you have to right click.
What?
Right click again.
All right, yeah. Click. Here we go. All right. So let me center this one. There you go. All right. As you can see, okay, let me increase that electric field coming out. So this is a good, I think everyone can see this, right? So let me zoom in here. So this, I can scale these electric field lines out to make it sort of like dramatic a little bit. So that's electric field that coming out from a positive charge. And that fainted sort of like a sphere over there that gives you a surface which is closed. It's a sphere, so it's closed surface. As you can see, if you could sort of go around over here, you can see that the net flux is going to be positive because it's trying to escape from this. And that means that is the evidence saying that I must have a charge inside at, it doesn't have to be, okay, in this case, it's so symmetric. So it's supposed to be at the center. All right. But if it's not, I can move this thing around a little bit. But no matter what, as you can see, as long as my charge is still within that closed surface, I always get net positive flux no matter where I move this charge around. See that? You still have net flux trying to come out from the enclosed volume. But if I move this thing outside, here we go. Now you start seeing that this simulation give you the blue. The blue is the influx. The red is an outflux. So as you can see, when you look at this one, you can see that, oh, Ajahn, there will be no net flux in this on this sphere because there's no charge inside. Out eventually must be equal to in. And that's what it is. That is the Gauss's law, saying that flux is one-to-one mapping to the charge. And we are done for today.
Okay.
Thank you for the simulation. Very good. And you guys can play around and take a look at this. I hope they have more. I think, yeah, they should have more.
They have the cube one.
All right, but this
Yeah,
one is good. You
really.
can sort of like exaggerate the electric field lines a little bit, so make it
Yeah.
even cleaner. Cool. All right, I can move things back to the center. Thank you. All right, guys, that's it for today. I hope you learn the key points today is about electric flux and ended with the Gauss's law. Next time we will apply Gauss's law to an actual scenario that make things a little bit more useful and talk about capacitor then. All right. Thank you for sticking around. I'll see you guys on Saturday if you can make it. If not, just watch for the YouTube video. Okay, guys. Thank you. Bye-bye. There's some sound over there.